Okay, so this is part 2, and I put the answers to the first 4 problems on video 1. So if you didn't get either 3 or 4 from the day before, you need to go back and watch that video, at least the end of that, to see the answers for 3 and 4. Second period did get, or ninth period did get that far, so that's why I went ahead and put all that on the first video. And so this one picks up on number 5. So if you missed any of 1, 2, or 3, or 4, go back and look at the other video. And we'll start on number 5. There were a couple of corrections that had to be made. I sent you an email on one. So if you were here, you need to watch that. All right, so here's number 5. They've got 3 reactions and 3 lattice energy, and the lattice energy for the first one. And we want to know, is the KCl, would the lattice energy for the KCl, the second reaction, be greater than or less than 788? And explain using periodic trends, I believe. Oh, periodic properties and Coulomb's law. So here we go. If you look at NaCl versus KCl, Na is in period 3 and K is in period 4. So K is a larger atom. Right, K is larger than Na. So that means when we're looking at Coulomb's law, oops, not equals. F is proportional to Q1, Q2 over R squared. When with K being a larger radius, then the R squared value, the distance between the sodium or the potassium and the chlorine, will be greater than between the sodium and the chlorine. So you get a greater R squared, and if R squared is bigger, then F is smaller. So lattice energy for KCl should be less than 788 because K has a larger radius. And that means that the F is smaller. Well, R squared is smaller. No, R squared is bigger, sorry. Which means F is smaller, right? Because R squared is in the denominator, so if it gets bigger, then F gets smaller. And we're looking at the force. So F is smaller. And that's why the lattice energy is less. Letter B, we're looking at the same thing, but it's MgCl2. And with this case, if you'll remember, Mg is right next to Na on the periodic table. They're both in period 3. So the radius difference, R squared, is not a big deal for the magnesium versus the sodium. What is a big deal is this magnesium is a +2 charge, sodium is a +1. So your Q1 value for sodium is 1, but your Q1 value on magnesium is 2. So it's going to be twice as much force. So lattice energy for MgCl2 should be greater than 788 kilojoules per mole because magnesium is a +2, whereas Na has a +1 charge, right? Greater Q1. Okay, so number 6, they're giving us the these elements, these atoms in the space below. Complete the Lewis dot diagram for S2Cl2 molecule by drawing in all the bonding and non-bonding electron pairs. Each sulfur has 6 valence electrons. Each chlorine has 7. So we got 12 plus 14 are for 26 valence electrons. So bond everything once. There's 6 of the 26. If I put an octet on each chlorine, so now we've got 8, 16, 17, 18. We need 8 more. 2, 3, 4, 5, 6, 7, 8. There they are. That is the finished product for letter A. Oh, no, that's not letter A. That's just completing the diagram. Okay, so there's the diagram. Letter A says, what is the value of the CLSS bond? So that's the bond between the Cl and the two S's. And if you'll notice, like, if we'll, let's say we're looking at this S as the center of that angle, right? The S has 4 electron domains, and 2 of them are bonds. So this is a bent molecule, but it's got 2 lone pairs. So the bond angle is going to be slightly less than 109.5. So we need a number that's slightly less than 109.5. How about we say 107? And based on your Lewis structure, what is the hybridization, sp, sp2, or sp3 of the sulfur atom in the S2Cl2? Well, it's got 4 electron domains, so sp3. And that's all that is. All right, on the next one, they give us the skeletal structure for the nitrite ion. We have to fill in all the bonding and non-bonding electrons. We need 12 for the oxygens and 5 for the nitrogen. So 12 plus 5 is 17, plus there's 1 because it's a negative ion. So we got 18 electrons to place. So if we bond everything with 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, then nitrogen does not have an octet. So we need to take a pair from one of the oxygens and make it a double bond with the nitrogen. And it doesn't matter which side you go from. So I'm just going to pick this side here. I'm going to put a double bond. And that takes 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. In reality, they didn't ask for reality, but in reality, we could draw it this way. Which means it would have a resonance structure. Hang on. Hello? Yeah. Yes. Yes. Yeah. Just one. He's the new boy. I can't remember his name right off the top of my head. Yes. Yes. Okay. Oh. All right. All right. Bye. Sorry, I had a phone call. So anyway, there should be a resonance structure there for that. Hopefully you recognize that right away. So letter A was approximate ONO bond angle for the NO2 that we drew. It's a 3 electron domains on that nitrogen, which makes it a trigonal planar, which would be 120, but the lone pair in the end reduces that a little bit. So something a little less than 120, I'm going to say 118. What do you think about that? And then based on the Lewis structure, identify the hybridization. Well, the N has got 3 bonding domains, so that means it needs 3 orbitals, sp2. And then do you predict the nitrogen-oxygen bonds for the NO2 should have the same length or different lengths? Justify your answer. Well, since there are resonance structures, it's going to be the average of those 2 bonds, right? Bond order 1 and bond order 2. So the bond order on average will be 1.5, so they will be the same. Do we have to justify that? Yes, justify your answer. Because of the resonance, because there are 2 resonance structures, the bond lengths are a hybrid or average. of the two bonds. So that should work. Okay, so that is number 7. Number 8, it's giving you this drawing, and it says the particle diagram is intended to represent a portion of a crystal lattice in LIF. Identify the error that is shown in the particle diagram. Explain how the particle diagram should be corrected to be a more accurate representation of LIF. Well, Li is at the beginning of period 2, but it's a Li ion, so it has lost its electron. So it's on the order of a helium atom. And the fluorine at the end of period 2 has gained an electron, so that makes it bigger than it should be. Actually, bigger than, well, it was already bigger than the neon, but it's bigger than it would have been otherwise. So we've got these flipped around. The F minus ions should be larger and the Li plus should be smaller. Number 9, we've got some questions about steel. We're talking about steel, which is iron with carbon mixed with it. And if you think about it, iron being in period 4 would be pretty big compared to carbon, which is in period 2. So this will be an interstitial alloy because the atoms are such different sizes, okay? So 9A should still be a substitutional or as an interstitial. We just answered that. Interstitial because iron atoms are much larger than the carbon. And then B, explain why high carbon steel is more rigid. Well, if you think about it, if you got these iron atoms and a carbon atom in between, that kind of helps to lock things into place. So the more carbon, the less flexible it becomes. So more carbon filling the interstitial spaces makes it more rigid. Oh, and just a point of clarification. Don't say it or they or them unless you tell them, unless they know exactly what it is. So I said instead of making it more rigid, I said the high carbon steel more rigid. Just don't leave anything up to their interpretation because they may not interpret it the way you want them to. Oh, there's the chart. Okay, so that is number 9. I think I'll stop here because this video is getting pretty long. And then I'll put 10 through 14 on the next video. Sorry about that phone call I took in the middle. I have no way to pause and restart these videos when I'm doing a screen recording, and I don't want to learn how to edit yet. So see you in a little bit on the next video.